Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the concept of surface when the surface is curved and that is submerged in the liquid. So in the previously already we have discussed few surfaces or plane surface like horizontal and vertical and inclined surface when it is submerged in the liquid. So here we'll discuss on behalf of inclined and vertical. Let's consider a surface which is curved surface. So already have taken the diagram of this. So this is the fluid layer, okay, or this is the water layer we can say, and there is a curved surface is there. This one, the curved surface is nothing but this AB is the curved surface, okay, and in the curved surface again we have taken a small area or small object in that very small that one. So there is a small object which is here, okay, and that area of that small object is dA, okay, and the force which is acting to that object is nothing but dF, okay, and this force will be always normal to the object, this one, and it makes an angle to the surface with an inclination of theta, you can say, okay. So these things previously we have seen only when the object is in vertical to the water surface or this surface, and when the object is in inclined, horizontal, this is horizontal case. So for that also we found the pressure force and the center of pressure for this, okay. So here also we have calculated, and again also we have seen when the object is in inclined condition, okay. So when the object is in inclined, so these are things we already have discussed previously, and for today we'll see when there is an object which is curved surface, okay, and when it is submerged in the static liquid. So this liquid condition is static liquid. So same thing we are going to calculate here. So first of all, let me tell you the force which is acting on the surface, or we can say the pressure intensity. We know that the pressure intensity on the, you can write on the surface, the pressure intensity on the surface of the small area dA, okay. So that one I can write. We know that pressure intensity formula is nothing but rho gh, okay. So this one actually the pressure formula what we know previously also, okay. Now what the pressure force acting on that dF, the pressure force, okay, we can see this one, the pressure force on the small dF which is acting on this perpendicular to this object on the dF on the surface, that is we can write, we know that pressure equal to, also we can write force by area, and the pressure force F equal to, we can write P into A. So these things already we know previously, okay. Now here dF we can write similarly P into dA, P into A. So A is the total area of this curved surface will be there, but for the particular the small object, the area what we have taken, that is dA, okay, that is the surface area of the small object. So that's why, so that will be dA, and this one again we can put the value, the value of P, that is nothing but rho gh. So that is nothing but rho gh into dA. So this one we can give one equation 2, okay. This is equation 1, this is equation 2, we can mark it. But the thing is, next if you see, up to this also we have done previously also, and we got the same thing, okay. This is dA, that pressure intensity formula rho gh, and this is the pressure force on the small area, that is nothing but rho gh into dA. But the thing is here, if you see, the force which is acting on this is perpendicular to this object surface, but the surface is situated inclined to the water surface. So this equation is not going to satisfy this condition, okay. This equation the pressure force which is acting on this, that is not going to satisfy for this condition. Why? Because it is makes an angle of theta to the surface of the water. Okay, that's why what we need to consider, either we need to consider you can do the resolve the force in horizontal and vertical direction. So what we'll do, so let's resolve the force in vertically and you can say horizontally. So that means the components what we need to consider here, one component, see dfx, which is acting on this, okay, and dfy, which is acting on this point. Okay, so that is, one is dfx, another one is dfy. So these are the two different components which is acting on the small object, okay, in horizontally and vertically. So this one, these are the two components which is acting. Now if you want to find out the resultant force for this, then the total force on the curved surface, previously what we used to do for this, we used to integrate this one. Now the total force for this, the total force on the curved surface, we can write F equal to, we know that the component of this x square, fx square plus and fy square. So this one we can give equation 3. Okay, this one we can give equation 3. Now again, when it is inclined, now we can find out the theta is here, the theta is here, this is also theta. Okay, this is the, okay, and if you see here, so this is the pressure force on the x direction, or this is the force on the y direction which is acting this one. Now we know that this is the force which was perpendicular to that object only, because it is a curved surface. Okay, so now this angle is actually theta, and this angle also we can say theta, because if you see, this is the perpendicularity, so total 90 degree will be there, this one from here to here, and this is theta, means this is 90 minus theta. Okay, and this is 90 minus theta, means as this is perpendicular, both are, you see, so this will be theta here. Okay, that we know already. Now the next thing what I can write here, and this is one thing, and also you can write, we know that one is magnitude, one is direction. So the 10 pi what we can write, that will be fy by fx. So this one we can give the equation 4. Now similarly, what I'll write, first one dfx, let's find out the dfx value here. So dfx, where it is, dfx is this one. So dfx, what I can write, the df is acting on this object perpendicular to this one, and that makes an angle of angle with a theta, okay, to this vertical one. And similarly this component, if I am resolving the x direction, that is df x equal to, I can write the force which is acting on that into sine theta. Okay, so this is one thing. So df already we know that previously, some formula we got, this one rho gh dA, so that one we can write rho gh into dA into sine theta. Okay, so this is one. Similarly dy in the sense dfxy, dfx this one. Now we can see dfy, the force resolved in the y direction. Okay, so that one we can write df cos theta, df cos theta. So that one we can write again, df value we can write here rho gh dA into cos theta. Okay, this is the equation for this. Now we can say the total force, okay, in x and y direction. Okay, so the total force which is acting in the x direction, and what is the in the y direction. So these forces we can identify from this diagram. So up to this I think you have clear. So because previously we have not there. That means we have previously we have the inclined surface, we have the vertical surface, okay, and horizontal surface. For that conditions are different. We used to find out the total moment of the force from this object to the surface layer, how much force is acting on that on the object, and what the distance is there. So we used to find out. Now for this here conditions are different. Okay, now the total force in the x and y direction is nothing but what we'll do here, we'll do the integration. So in the integration of dfx, integration of, we can write rho gh dA, and this is sine theta. Okay, so now this dfx, integration dfx, we can write fx, and equal to, we can write let rho g keep it outside, and integration of, we can say hda into sine theta. Keep one equation, suppose 5 here. Okay, this is for the x direction, the total force in the x direction. Similarly, I can write the total force in the y direction is nothing but integration of, again, dfy equal to, the formula is there, rho gy dy, I hope the same, rho g h, sorry, rho g h, write it again, rho g h and dA, and this is, I think, cos theta. Okay, and here also same thing, we can just keep it this rho g constant term outside, and integration can write rho h dA cos theta. So this is equation 6 we can give. Previous one I have given 5, so this one we can give 6 one. Now let go to the diagram here. Okay, now if I draw a diagram, let it draw it here. Okay, so this is the diagram here, and which is a triangle, and this triangle came from the previous one. Okay, so let's see, this is the E, and this is the F, and this is the G, and I can say this is the theta, and this is the side which is dA. Okay, and I can write, this is a curved surface, suppose, let's consider it. Okay, the curved surface in that. So this will be our dA sine theta, and this will be our dA cos theta. Okay, so this is the the triangle we can get from that. Now yeah, this triangle actually we got from this only, from here only. Okay, that's why I've taken outside and I've drawn this one. Now if we see the triangle here, EFG triangle, let's see, from this triangle EFG triangle, we can write EA equal to DA, this one, this triangle EFG, we can write EF equal to DA, and similarly we can write FG. FG is nothing but this one, vertical component of this, so that one we can write FG equal to DA sine theta, and similarly I can write EG equal to this is here DA cos theta. Okay, now this previous equation, if you see, we have already DA cos theta, and one more previous equation is there, that is DA sine theta is there. Here DA sine theta is there, and here DA cos theta is there. Now we can put this value on that point. Okay, so what we can write, DA sine theta EG. Okay, so there we can get the value, the vertical component we can write in that. So the equation, previous equation what we got there, so there we can write DA sine theta equal to, that is FG. Okay, which is nothing but the vertical projection. You can say this is vertical projection. Okay, vertical projection, this one, vertical projection of the area. Which area? The DA, this small area of area DA. Okay, so the expression we can write here now, that is how much we can write. So the previous expression, previously we got rho g HDA sine theta, So that one I can write HDA sin represents. Okay. So this expression rho g h dA and sine theta. Okay. So this expression actually it indicates that the total pressure. Okay. The total pressure force. The total pressure force. Okay. On the projected area of the curved surface. On the projected area of the curved surface. Okay. So we can write the Fx equal to, because this is the Fx component was there, this is the formula Fx component, so this one Fx we can write okay, nothing but the total pressure force, okay, on the projected area, on the projected area of the which surface, in the curved surface, of the curved surface, on the vertical plane. Okay, so this is the concept of this Fx. Similarly, we can see this is about the x component. Similar y component is there. For the y component, what we got here, the Eg, that is dA cos theta. Okay, so this dA cos theta is nothing but similarly what we got here, we can say, let me see, this is dA cos sin theta, Fg is there. Now similarly Eg we can write, Eg already we have written here, Eg equal to dA cos theta. So that is also nothing but what, the vertical force, or you can say this is the horizontal one. So the horizontal projection, or you can say this is the horizontal component of this upward of this curved surface dA. Okay, so this one we can write, dA cos theta, which is nothing but what we got there, Eg. This is the horizontal projection of the dA. Okay, horizontal projection of dA, that already I told you in this diagram. Okay, now also we can write again integration of this rho g integration of HDA cos theta. Okay, so this is the thing, is the total, this thing is the total volume that content, the total volume content between the curved surface, the curved surface, this one we can write in such a way, this is the total volume content between the curved surface, okay, which is extended up to the free surface, which is extended up to the previously if you see this one is extended up to the free surface, extended, okay, no need to write, actually I'm telling, extended up to the free surface. Okay, now this one again what we can mention it, so this total force, or we can say this one, the rho g integration of HDA cos theta, also I can say, okay, this is the total equal to, I can say, the total weight, okay, the total weight supported, okay, supported on the curved surface, the total weight, okay, supported on the curved surface. So that is nothing but, write this way, Fy equal to integration rho g integration of HDA cos theta equal to the weight of the liquid supported, okay, supported by the curved surface, okay, supported by the curved surface, this one, okay, this one we can explain in this way, Fy equal to rho g integration of dA HdA cos theta, this one. Okay, that is nothing but weight of the liquid supported by the curved surface up to the free surface of the liquid, up to the free surface of the liquid. It's very simple. Okay, now see, this one we got what? Fx equal to the total pressure force which is projected on the curved surface, okay, up to the vertical plane. Okay, now, and this one is the total weight of the liquid supported by the curved surface. Let me explain again here. Now if you see this diagram, now see, this is the our horizontal component what I told you. So the total amount of fluid which is present here, the total weight of this liquid is supported by this. Okay, and that vertical component which is there Fy, so that is the force acting on the curved surface. Okay, so that is the only meaning of these two things, two concepts. One is Fx and one is Fy. So here we don't need to identify any kind of center of pressure and other things, because this is a curved structure. So I hope you understood how to this. If you are having any doubt on this, you can give a comment on the comment box. Thank you all.